Okay guys, we are live. So hello everyone, and in this video we'll be learning about tree data structure. It's not tree TREE, it's TRIE. So I'll just call it trie data structure. Okay, so it's trie data structure. And how is it different from tree data structure is actually uh, if we talk about binary search tree, it was taking two nodes at max, right? But in trie data structure we can have n number of nodes for each parent node. Okay, so how are we performing insert and search? That's a very complicated task, and you might be thinking, yeah, if I want to search anything, if anything has n number of child, search will be difficult. But not in this case. We have some specific rules, and it's really helpful in one very important feature which we use on daily lives, that is autocomplete on any search engine. Okay, if you talk about Google search engine, it also uses trie data structure, and obviously there are more complications and rules in that, but it's a basic uh, autocomplete feature, and it's using trie data structure. Okay, so we'll see what's the usage of that and why are we giving it so much importance. Okay, so let's begin. So what I'll do is I'll just give you a very basic example so that you get an overview of trie data structure, and you know that this is really beneficial for us. Okay, fine. All right, so let's begin. And what I'll do is I'll just give you an example of a few alphabets and words. Okay, that means if you want to create a dictionary, there are actually a few methods in JavaScript you can create a dictionary, but searching is not easy in that dictionary because suppose if you want to search a word named as ball, so ball can be stored as an individual word. Okay, individual word. So it's very difficult to find ball one by one. It will look into the whole array or any set you are talking about, then the ball word will be found. So it's very difficult. So trie data structure solve this problem. Okay, it actually creates the prefix notes. It actually remembers the prefix notes. What I'm saying is, suppose I'll give you an example. I'll give you an example. A very basic example which I saw today is, suppose I have a few set of words. Okay, I have a few set of words, and let's name it as, yeah, let's name it as app. Okay, suppose I'll just write separately. Suppose the first word is app. Okay, second word is apple. I'm talking about insertion. Okay, I'm talking about insertion. Suppose I am creating a trie data structure in which I am inserting these words. Okay, so app, apple, and uh, if I take another word named as apply, and let's say another word which starts from banana. Okay, and I'll just say that another word is bit. Okay, so you can see that we have these words. Okay, so obviously you can have around 26 initial letters of English alphabet. That means there can be 26 different alphabets which will be your starting. Okay, suppose a word can start from either a word can either start from either b, c, etc, etc. Okay, till 26. And if I talk about any other alphabet language, like if I talk about Bengali language, I think there are 50 alphabets by which any word can start in their language. So let's talk about English. So there can be actually 26 nodes. So let's take an example of only these number of nodes. Okay, these number of alphabets. That means we have two initial alphabets, a comma b. Okay, right now we have two initial alphabets. So what would happen is, first of all, we'll be having a root node. Okay, you can assume it as an empty node. Okay, here what will happen is, first word comes app. Okay, so what will happen is, first a will be here. Okay, then we can similarly create, there isn't any foundation that one thing must be left child or right child. There isn't any foundation in this. Okay, so you can write it any order. So a, then we inserted p. Okay, then we inserted another P. So you can see that we have inserted this word very easily. Okay, it's a very easy operation, just you need to insert it. Now the best part of trie data structure is, suppose you want to insert apple. Okay, suppose you want to insert apple, so what would happen is, since you inserted app, so whatever is the last word will be actually having a and node. Okay, so it will be helpful in searching. Okay, it will be helpful in searching. Okay, so now next time what will happen is, suppose if you want to if you want to insert apple, if you want to insert apple, what would happen is, a already exists, P already exists, P already exists, and then I can insert L, and then I can insert E. Okay, again I can put it as a star, the endpoint will be a star. Okay, that means whenever we are searching apple, we'll see that suppose I want to ask that this tree is containing AP or not. No, AP, I mean, if AP suppose is a valid word, okay, suppose if AP is a valid word, this tree contains AP or not? No, it does not contains EP. If suppose this P had a star, if in any case this P had a star, that means in insertion, if we had a word named as AP, if we inserted that word, that in that case we'll get AP. But we didn't insert AP, right? We didn't insert AP, we inserted APP or APPLE. That means we don't have a word like AP. Okay, we don't have a word which is AP, so it will return false. This will be not be the case. Okay, this will return false. So if I call APP, sorry, if I call AP, it will return false. If I search AP, it will return false. If I search for APP, it will return true. Okay, it will return true. That means app exists. If I talk about APPL, it will return again false. Okay, I hope you are getting it. That's why we are pointing the ends as a star. Okay, you can just remember this. We'll be remembering the endpoints with something. Okay, so APPLL is not existing here. Okay, similarly we have APPLE. Okay, APPLE, and it does not exist. Sorry, it exists. Okay, so it's true. Okay, so you can see that this is a very basic idea of how we are inserting words and how we'll be searching things. Okay, so searching is very easy in this case. As you can see that any alphabet starting from A will always be starting from this path. Okay, any alphabet, any word starting from B, okay, any word starting from A will be starting, it will be in this path. You can have n number of branches here also, because A can have 26 more alphabets. Okay, A can have 26 more alphabets. It's like that. Okay, so you can create, actually you can create a whole English dictionary with that, and then you can find that is that word valid or not. You can also use it for autocomplete feature in any search engine or anywhere you like to do. Okay, so it's very helpful data structure. And now let's talk about some other word, that is we have banana and bit. Okay, so I would say that second is banana. Okay, so again you can create as it is, because we don't have any word for B. Okay, BANANA. Okay, that's it, very good. And then you need to see that the next word is bit. So when the bit comes here, first you need to check that in the first level A exists, right? B exists. Okay, so we need to check for the first letter, that is B. Yeah, B exists here. You can see that, yeah, B exists here. Okay, B exists here. So what will happen is, after B I'll see that the second is I. Okay, the second alphabet is I, so we'll see that BI exists or not. No, BI doesn't exist, so we'll simply create I here. Okay, by the way, we must mark the endpoint as a star. Okay, the star. Okay, so this is the endpoint again. And then if I talk about the next thing, that is T, next alphabet, that is T, I'll just mark T here. Okay, okay, now if I mark this as star, that means this is the endpoint. Okay, suppose now there is a new word named as byte. Okay, BITE. Okay, byte. So for byte, you will see that first of all you will see that B exists on the first level or not. Yeah, B exists on this level, first level. Then we'll see that I exist on any other level of B. Yeah, I exist on the second level of B, so you can see that I exist. So then we'll go to T, that means T exists on the third level of, that means I can have some branches, right? B also can have some branches. That's how we are looking. So in one branch I exist. Okay, in one branch I exist. Then we'll move forward, we'll see that in any branch of I, T exists or not. Here T exists. okay, T exists. Then we'll move forward, we'll just see that either E exists or not. No, in this case E doesn't exist, so we'll create a new branch named as E, and what we'll do is we'll simply mark it as an endpoint. Okay, so that's how we perform insertion in any trie data structure. And now if you want to search, suppose you want to search banana, we'll see that yeah, B exists, okay, then A exists, then N exists. We'll be actually performing a loop operation, okay, then A exists, N exists, and then again A exists. And then when we are out of the letters, we are in the last letter, we need to check that current letter has an endpoint or not. If it does not have an endpoint, that means that word doesn't exist. Okay, if I talk about AP exists, but if I stop at P has an endpoint or not? No, P is not having an endpoint. This P is not having any endpoint. Okay, so AP is not a valid word in this alphabet. Okay, so that's how things work. So that's a very basic overview of how trie data structure works and how trie data structure is created here. Okay, so I hope you got the idea. We can actually assume a few more operations later on. So okay, so now I think that you are ready for a formal definition of trie data structure. So you can actually visit Geeks4Geeks. You can actually visit this article, and here you'll find that yeah, they have given a formal definition for that. So trie is a type of key array search tree which is used for storing and searching a specific key form set. Okay, so actually these nodes, one node, second node, the second node, third node, these are all nodes. Okay, these are actually stored in key value pairs. Okay, so one will be the key, that means the nodes whatever will be the key, and its value will be A, its value will be B, its value will be C, something like that. Okay, so we'll be seeing that. So now using tree, search complexities can be brought to optimal limit. As you can see that if I want to search apple, I'll go to this path. Okay, I'll go to this path. If I want to search for banana, I'll go to this path. If I want to search for bit, I'll go to this path. If I want to search for byte, I'll go to again the same path. Okay, it's like that. Okay, so I hope you are getting this. And yeah, if I want to search for byte, I will still go to the same path. Okay, so searching is very easy as we have some amount of path. Obviously there are huge amount of paths, but exactly we'll know exactly that if the word is if the word is starting from A, we'll follow one path. Okay, if the word is starting from B, we'll follow another path. Okay, if the second, we talk about banana, if the second word is A, so we'll follow path which has B as first word and then second word as A, that means this one. Okay, that means this one. Okay, it's like that. So very easily we can search things in this kind of data structure. Okay, so a tree data structure is a multi-way tree data structure used for storing strings over an alphabet. Okay, in most cases you will be storing strings, or you will be storing a set of alphabets like words. Okay, so it is used for storing a large amount of strings. The pattern matching can be done efficiently using tries. Okay, that means suppose if you are implementing auto search, okay, autofill, okay, autofill, then you can simply assume it as a trie data structure. That means it's using the autofill feature is actually using the trie data structure. Okay, so the tree shows words like a lot, alone, and these are different kind of words. Just don't go to these specific examples. You can assume it as a set of different any number of words. You can store it as any number of words. Okay, so the idea is that all strings sharing common prefix, okay, should come from a common node. This is a very important line. They have mentioned that common prefix should come in one branch. Okay, you can see that if I have any word starting from app, there will be one path, that means one branch. Okay, then there will be sub branches also, but yeah, the common prefix is always remembered and the path is always followed that way. Okay, so the trees are used in spell checking programs. Again, the same logic as if you want to check the spelling, like if ap is a valid word, no, ap is not a valid word, app is a valid word, yes, app is a valid word. Okay, so that's how you can just spell check. Okay, so a trie is a data structure that supports pattern matching queries. Okay, so here you can see that they have given a diagram, so you can check that yeah, you can check that this is also a good diagram, but I would say that you must try your own diagram so that you get a better idea of how things are working. Okay, you can create a set of different matching letters, like if I talk about some other example. Okay, let's take some other example. Okay, so suppose if you want to try, this is your homework. So an is a word, ant is a word, okay, and is a word, okay, Android is a word, okay. So let I have taken some words from A, and then I'll say that take some words for B. So B, okay, B double E, okay, honey bee, okay, and I'll just say beyond, because. So I've taken some words from B, and similarly you can take some words from C. Okay, so I'll just say uh, can, cat, cake. Okay, so you can actually create some n number of words. Okay, so again you can have infinite number of words here, you can have infinite number of words here, and you can have total 26 here. Okay, total 26. That means from A, B, C till Z. Okay, if I talk about English alphabets till Z. Okay, you can create these kind of things. Okay, so if you want to store a whole dictionary, you can actually store it this way. And then if you need some spell checking, obviously you will be performing search operation, and you'll find that if I talk about some specific words, like if I haven't stored a word named as AP in my dictionary, that means it's not a correct word. Okay, it's not having correct spelling. Okay, so we can actually give suggestions that yeah, you can either try this spelling or something like that. Okay, so you can create some logic with that, and you can draw tree using these examples. Okay, so these are very basic examples, and you can implement the same logic which I have implemented here. Okay, so I hope you are getting this, and this is actually your homework. You can use these some set of words which I have given to make a try. Okay, try, not tree, try. All right, so I hope the basic logic is clear. Now we'll be actually creating a tree out of a trie data structure. Okay, we'll be creating a tree out of trie data structure. We'll be writing its code. Fine. So let's begin. So before moving on, in the live chat, you'll find a course provided by Geeks4Geeks. That's for data structures and algorithms in JavaScript. You can check out this course. This is a paid course, and if you are a beginner in JavaScript, you can check out this course. And some people are actually looking for some easier language for learning data structures and algorithms. So if you want to find an easy language, or if you are opting for web development and you want to become more advanced in web development, then obviously you will need JavaScript and advanced JavaScript data structures. You can check out this course. Okay, so all the basic details of this course is available here. You can see that these modules will be covered. We'll be starting from introduction, then mathematics, then bit magic, and then all the things which are required for DSA in any kind of language. Okay, not just JavaScript. You can use these operations on any kind of language. The logic is same, the concept is same, and I would say the syntax is a bit different in other languages. But yeah, all the logics can be applied in any other language if you later on learn in any other language, or if you know data structures and algorithms in any other language, you'll find this course very easy. Okay, so now we can continue. All right, so for the code, you can check out this course. You can check out this code for getting the code, but I would say that I'm creating my own code, so you can check my code also, because mine is easier one. Okay, so I'll be providing that. But yeah, this is a very great article, and you'll get a more better idea what's actually happening here. Okay, and since we are talking about JavaScript, so you need to select JavaScript here, and you'll find things are easier. Okay, so they are actually taking 26 alphabet size, but we are, in my case, what example I'm giving, I won't take any limit. Okay, that means the array size can be any, you can store any number of alphabets, it's not any boundation. Okay, so actually in JavaScript there isn't any boundation with the array size. You can either create 26, you can increase it at any point of time. Okay, so yeah, you can see this example also. This is a great example. They have performed insert operation. They have actually first created a try node. Okay, first created a node, then they have performed insert operation, then they have performed search operation, and yeah, they have done it like that. But yeah, I'll be using a different approach. Okay, fine. Also, yeah, you can see that there are some time complexity which are given here. You can see time complexity of trie data structure is big O of n, and searching is big O of n. Okay, so it's much, actually it's much lesser than other kind of dictionaries, or if I talk about normal arrays for storing words for searching. Okay, so it's a lit lesser. Okay, it's lesser because you are actually performing operations on a non-linear data structure. So a non-linear data structure is always having some branches. Okay, it's always having some branches. So searching is a bit complex, but definitely it's much lesser than a normal linear data structure. Okay, it's taking less time than a normal data structure. Okay, so now I'll just close it, and I'll be opening VS Code here. Yep, fine. So let's create a file named as script1.js, and here I would say that let's write a node first, then we'll be performing insert operation, then we'll be performing search operation here. Okay, so let's say that initially we okay, just a minute. Also guys, if you haven't watched my previous videos of the same playlist, you can visit the Geeks for Geeks practice channel. First of all, you need to visit the Geeks for Geeks practice channel, and here you would find that in the playlist section, all the playlists are available. You can see that you can search for this data structures using JavaScript. In this playlist, all the videos are available. You can watch all the videos to get a more better explanation of all kind of data structures which I have taught till now. Okay, fine. So now we can continue. Yep. Hmm. Okay. So first I'll be writing a code and then I'll make you understand what's actually happening here. Okay. So always you would assume that initially any node will be having some children. Okay. What I told you in my example is the first node is blank. Okay. First node, you can consider the first node as blank, or let's say it's null. Okay. It's null. And then you are having, instead of null, I'll just say that it is blank. Okay, then you are having some childs. Either you word will be starting from A, either word will be starting from B, either word will be starting from C. Okay, that means these are the children's. Okay, these are the children's. So what I'll do is I'll check that my parent node is having how many children's. Okay, then I am about to perform insert operation, then I'll see the same things which I have seen here. Okay, that means if A already exists, then I'll move in this path. If B already exists, then I'll move in this path. If C doesn't exist, so I'll create a new path starting from C. Okay, it's like that. That means I'll create a new child starting from C. So that's how we can create n number of childs. And if you're talking about English alphabet, you can create total number of 26 childs here. Okay, 26 alphabets, 26 children. Okay, so that's how it works. All right, so what I'll do is I'll be creating a class named as try node, and inside this I would say that we have a constructor. First constructor will be called, and initially the you would say that the children will be always, whenever you are creating a node, their children will be always, there will be no children if you create a node. Suppose I create a blank node, that means if I talk about this first node, its children will be initially null. Then you'll insert a word starting from A, then you insert a word starting from B, then you insert a word starting from C. It's like that. Okay, so initially the children of any node, if I talk about a node named as A will also become a node. A does not have a child initially. Okay, if I insert another word starting from A, then followed by some other alphabet, then there will be some children. Okay, so it's like that. Okay, so initially there will be no children, and then I would say that this dot is end of word. Okay, so this is actually the pointer which we will judge for search operation. This is very important. So whenever you are inserting things, the last alphabet of your word will be having this as true. Okay, initially everything will be false. Initially each word is having, suppose, four alphabets. All four children, all four alphabets will be having false. Okay, is end of word as false. Okay, so it's like that. So initially everything will be false, and whatever is the last alphabet of your word will be marked as true. Okay, so is end of word is as false initially. Okay, that means I'm simply saying that whatever is my node, that means, suppose I'm talking about node A. Okay, this is not a children, I'm talking about it as a node. Okay, I'm thinking of it as a node. I will assume that it's not the end of my word. It's not the end of my word. There can be more alphabets in it. Okay, apple, app, something like that. Okay, so we'll see that. And this is the same which I told you here. Okay, this is the same which I told you here. Whatever is the end will be marked with star. That means will be marked as true. Okay, whatever is the end will be marked as true here. Okay, so that's how we'll be doing things. And here what we have done is we have created a very basic structure in which the children and end of word is false. Okay, now we'll be creating a tree. Now we'll be creating a tree out of that node. Okay, this is a simple node. This is a very basic node which we have created. Now we'll be creating a tree out of it. So a tree will always be having a root node, right? Will always be having a root node, and a root node will be just this dot root, and it will be a very basic node. Okay, very basic node which has no children and its end of word is false. Fine. Okay, so first initially we'll be having a root node starting point. Okay, you can assume this as the starting point, and we are talking about this in here. Okay, so now what I'll do is we need to perform insert operation. Okay, so I'll simply say if I want to insert any word. Okay, so insert function will be called, insert method will be called, and inside this you can actually provide the word which you want to insert. Suppose I want to insert a word named as, suppose I want to insert a word named as app. Okay, so app will be actually provided here. App will be provided here. Okay, so now app has been provided here. What will happen is, first of all, I'll get my current node. Current node is what? Initially we are here. Okay, we are here, so this is my current node. Okay, so here I would say that let current node equals the root node, right? The root node, that means the top one. The top one is the root node and it does not have any children. Okay, so now what I'll do is I'll check that if it has a children, that means if it has a children a, then we will move further, else we'll create a children named as a. Okay, I hope you're getting this. If a didn't exist and I want to insert a word starting from a, that means app. Okay, then what I'll see is my root has a child a or not. No, in this case it does not have a child starting from a. So what I'll do is I'll create a child starting from a, then I'll move further. That means I'll check that if a is having a child starting from p or not. No, in this case it does not have, so we'll be creating p. Okay, we'll be creating p, and we'll also check that if p is end of word or not, if a is end of word or not. No, a wasn't end of word. How we will judge is if a is end of word or not? We'll be performing loop operation. Okay, we can get the length of string and then we can find the last word. Okay, last alphabet, sorry. So we'll see that a is not end of word, so it's false. Okay, its end of word is false. Then we have, again we'll see that this p is having a child p or not. No, it didn't had a child p, so we created a child p, and then this is the end of word, so I'll just mark it as true. Okay, so now it will simply remember this app as a word. Okay, this tree will remember app as a word. That's it, that's how things work. Okay, so here what I'll do is I'll simply create a for loop. Inside this I can simply say let I equals 0, and we'll be running it till the length of word. Okay, length of word is actually word dot length. Okay, whatever is your word, so word provided is suppose app, so its length will be 3. Okay, so it will run from 0 to 2. Okay, that means 0th index to 2nd index. Okay, 0 1 2 3 times, so length I plus plus. Okay, so this is a very basic loop. Now inside this, what do we need to check is, first of all, we'll get the zeroth word. Okay, zeroth word is what? If I am taking the example of app. Okay, if I'm taking the example of app. Okay, I'll just cut this, and if I'm taking the example of app, what will happen is zeroth I equals 0 simply means that we are talking about a. Okay, we are talking about a. Okay, so what would happen is, if we are talking about a, that means we are character a, so we'll be just storing it as here. Okay, so I'll just say const char equals the word which we are at. That means it's storing a. Okay, it's storing a initially. Fine. Okay, because we are at 0, initially we are at 0. If we were at 1, it would actually store p. Okay, it would actually store p. If we were at 2, it would actually store second p. Okay, so it's like app. Okay, fine. So this is very basic string operation. Now we are having the first word here. first alphabet of the word here. Okay, if I equals 0, then I would say that if my current node is what? My current node is actually empty. Okay, my current node is actually empty. Okay, initially it's empty, right? You can see that the top one is empty. What I would do is I'd simply check that this empty node is having child A or not. Is having child A or not. No, it does not have child A or not. So here what I'm doing is I'm passing a condition. If the current node has children which starts from character, okay, which is actually from a character A, okay, which is actually a character A or not. So we'll simply provide A here and we'll check that if it exists or not. So if it does not exist, this condition will be called. If it does not exist, this condition will be called. What we'll do is we'll create another node starting from A, and this is actually the children of our parent node. Okay, this is actually the children of our parent node, child of our parent node. Okay, so I hope you are getting this. And what I'll do is, yeah, I hope you are getting this now. Okay, so here you can see that is very easy. Here we have provided it as a child. We have simply provided a child because it wasn't a child before. We created a child, new child. Okay, and obviously it's not the end of word, so still it's false. Okay, end of word is false. So here what I'll do is I'll simply say that current node dot children, current node dot children, and whatever is the character, we'll simply make it as the node. Okay, what will happen is we'll simply create a child starting from A. Okay, we'll create a child starting from A, and we'll also mark it as a node. We'll also make it as a node because we want to move further. That's why we're creating as a node. Okay, so it's like that. So we are moving further also. That's why we are creating it as a node. Okay, so it's actually created a child A, and also created as a node. Okay, fine. So now what would happen is again now we have created a child A. Okay, we have created a child A. Now we need to check for second alphabet, that is P. So for that we need to shift our current node. Current node is this. Okay, we need to shift this current node to this child. Okay, so what we'll do is we will simply shift it. Okay, so what I'll do is current node is actually we shifted this from A, from blank to A, from root, from parent, from root to A. Okay, fine. And similarly, if I move next, I'll move from A to P. P will be the next root. Okay, similarly, it's like that. Current node will be P, current node will be P, current node will be L, current node will be E. It's like that. It will be moving later on. Okay, so now the first loop is complete. Then I will become 1. I will become 1. So what would happen is now we are at P. We are talking about P. We'll simply check that what is my current node. Node is now A. Current node is now A. What I would check is A having a child P or not? You can see A does not have any child. Okay, what would happen is I'll simply create a new child starting from P. Okay, what would happen is I'm creating a new child starting from P. Okay, that's it. Very easy. Okay, so we have created a new child starting from P. Okay, so it's like that. So again we have created, and then we'll shift our pointer to the next parent. That means initially it was here, then we shifted it here, then now we are shifting it here. Okay, so now the next pointer current node is P, and now we are talking about the third, sorry, now we are talking about the third element, that means the second index. Okay, so again the second index is also P. Now what I check is this is a current node. What I'll see is this current node is having any child P or not, for this case. Okay, so it does not have any child P. So what would I do is I'll simply create a child P here. Okay, I hope you are getting this. So I'll simply say that it's having another child as P. Okay, so it's like that. First it checked for A, then P, then P. Okay, so now it's like that. I have created a child, then I moved my pointer. Okay, when I moved my pointer to this P. Okay, I moved my pointer to this P. Okay, so now the problem is the loop is completed. Okay, the loop is completed. So once you move the pointer, it won't run the next time. That means we are on last alphabet, so what I do is whatever is the last alphabet will be my end of the word, right? This is the end of the word, so I'll simply mark it as end of word as 2. Okay, I'll simply mark it as end of word as 2. So once the loop is complete, I can simply say that current node is actually the end of word, whatever is the current node, it will be having the end of word as true. Okay, we simply made initially it as false, we declared it as false, but now we'll declare it as false. Now we will simply declare it as true. Okay, we'll convert it as true. Whatever is the last word, we'll be having the current node for that. Okay, we'll be having current node value for that. We are simply shifting again and again, and we'll just make it true. Okay, so now the word is complete, and we are also having some childs. Okay, so suppose if I talk about the next kind of word, that is apple. Okay, if I talk about apple, apple. Okay, so initially what would happen is the current node will be again starting from blank. I would look for the first alphabet, that is first alphabet is A. Okay, I would say that is my current node, parent node, is having child A or not. Yes, it has child A, so this will be skipped and this will be pointer will be moved towards A. Now what would happen is the pointer is moved towards this A. Okay, now pointer is moved towards A, so you are here. Okay, A is now the current node. Now again, for the next case, I will become 1 and it will become P. Okay, it will become P. So again, I will check that is A having P as child or not. Yeah, A has P child, so it will move the pointer to P. Okay, that means this if condition won't be followed, simply it will move the pointer to P. Okay, move pointer to P, and then I would again check that for the next input, I will actually become 2 and then again P. Okay, again P. So from this P, the pointer moved towards P. I would check that is it having a child P or not. Yes, it has a child P. Yes, it has a child P. So I'd simply check that yeah, it has a child P. So I'll simply move the point towards the next P. That means now we are in this P. We are in this P. Okay, we are in this P. That means the current node is now the last P. This P. Okay. Now we'll check that what's the condition for this. Okay, we'll simply check that if L exists for this last P or not. If L exists for this last P or not. No, it does not exist. So what would happen is I'll simply create a child and then move that pointer. Okay, so move that pointer to L. Okay, and I would also create the child. Okay, okay, so I have simply created a child. Okay, so now what would happen is we need to check for APPLE. Okay, that means I equals 4. Okay, so now what would happen is we are at L. We'll simply check that L is having E child or not. No, it does not have E child, so we'll simply create a child as E. Okay, and we'll also mark it as true. That means we are simply creating a child as E. We are shifting the current node to E. Okay, we are shifting the current node to E, and since the loop has ended, we'll simply say that the current node is having end of word as true. That means this E is actually the end of word. Fine, I hope you got this, and similar is for other kinds. So this is the easiest explanation which I have given you for any insert operation if you perform in the trie data structure, and nobody would explain you in this much easiness. Okay, fine. So similarly, you can actually do the same in search operation. So suppose if you want to search a word, what you would do it, you'll simply check that suppose if I want to search for apple, I'll simply check that if it is having a child or not. If it does not have a child, I would simply stop. I won't create a new child. Okay, it's different. Okay, the search is a little bit different, but yeah, logic is similar. Okay, so what would happen is in search again, I would start from the parent node. Okay, parent node, that means the root node. Okay, blank. Then I would check that if I want to search for apple, I would simply check that if this is having a child A or not. If it does not have a child A, I'd simply exit. That means apple does not exist. If A does not exist, why would apple exist? Okay, simple. So what I will do is I'll simply say that if it does not exist, if the child does not exist, you can simply just copy this. First of all, you need to start a loop here, same loop here. Okay, then here you would need to check that first of all you need to get the first word, first alphabet, that is A. Okay, we are at A. Okay, fine, we are at A, and we need to check that is my current node, that is the parent node, is having child A or not. If it does not have child A, that means apple won't exist, right? So what I do is I'll simply check that if my parent node, root node, okay, is having child A or not. If it does not have child A, it's not having child A, I would simply return false. That means I'll exit the loop. Fine, I'll simply exit the loop. That means here you can simply say word not found. Okay, word not found, will simply exit the loop because A does not exist. Why would P exist, PPLE exist? Okay, because A is the branch. The branch doesn't exist, why would its children exist? Fine. So this is for the case if A does not exist. If A exists, then we'll simply shift the current node. It's that easy. Okay, if it's that easy. So it's fine. Now once we reach the end, if the end of the word is true, then only your word is found, right? If I talk about appl, it's there, okay, it's there in a tree. Appl is there in a tree, but l is not end of the word, okay. L is not marked as the end of the word, okay. We are simply marking the end of the word when we are performing insert operation. That means appl exists, but end of word is false, so we are simply returning this end of the word as false. That means this word doesn't exist, appl doesn't exist. But apple, e is the last word, and last word is true, sorry, last alphabet is true, so it's simply returning true, okay. It's simply returning true, okay. That's it. We were setting values, and here we were simply searching values, okay. So that's how search operation works. It's very same as insert operation, okay. First we were searching for, suppose we are searching for apple, so current node will be blank, so I'll just mark it as blank. And then what would happen is, we are in the initial word I equals 0, so initial word is a, okay. We'll simply check that this root is having child a or not. Yeah, it has child a, okay. Suppose we have a word starting from c, cat, okay. Suppose we have a word starting from key. We want to search a word cat in this tree. You can see cat doesn't exist, as c doesn't exist, okay. C doesn't exist. So what would happen is, simply for this parent I would say that c exists as a child or not. It does not exist as a child, so I'd simply return false. That's it. What I've done is, I'll simply return false. If c exists, then I'll shift my pointer to c, then I'll say that a exists as a child for c or not. No, it does not exist, so I'll see that, okay. If a exists, then I'll move forward, my pointer will be at a, and I'll check for t. If t exists, then I'll simply check that if it's the last or not, okay. If it's the last or not, if its end of word is true or not. If its end of word is true, then it will simply return true, else false will be written again, okay. False is written, that means your word doesn't exist, okay. So it's like that. So now what would happen is, I'll simply create a tree here. So I'll simply create a tree here, try here, okay. And here I'll just insert a few words, try dot insert apple, try dot insert, what we can do is, yeah, we can actually insert it in, okay. First I think we should insert app, then apple, then try dot insert, and here what I'm trying to insert is apply. Okay, fine. I have inserted 3 words here, and let's check if it works or not, okay. So what I'll do is, I'll simply check for this app, okay. First I'll check for this app, so I'll run this, and here you can see try dot, okay. The problem with here is s, okay, fine. So let's run this again, so you can see that, yeah, app exists. Now if I mark again another p here, you can get false here, okay. That means it doesn't exist. So if I only want ap here, so you'll see that ap is not a word, so it will return false. If I only mark a here, it's there in a tree, but it's not the end, okay. A is not the end, okay. That means it's returning false, okay. It's fine. So suppose if I start a word from cart, okay, I'll see that here you can see that we have false, okay. So searching is perfect, and insert is also perfect in try operation, okay. So I hope you understood this concept, and this is a very easy concept. People make it difficult, but this is a very easy concept, and if you are learning things in JavaScript, they become much easier, okay. So I hope you understood the concept. If you still don't know how we are performing this, first you watch the introductory part, the explanation part, which I have drawn on whiteboard, okay, in the same video. Then you can watch the code part, you will get a better understanding, and it's the best explanation you'll get in any of the YouTube video, okay. So I hope you got this, and that's it for this video. If you have any doubts, you can ask me on the live chat. All right, so before ending this video, you can actually visit a course provided by Geeks4Geeks on the live chat, or you can check the same course available on the description, okay. So it's a link, and it will take you to this page. So it's a course by Geeks4Geeks for data structures and algorithms in JavaScript, okay. So if you want to learn data structures and algorithms in JavaScript for any reason, like if you are a beginner and you want some easy language, you can pick JavaScript. Or if you are a web developer or app developer and you are using JavaScript for your development purposes, then you would always need data structures and algorithms for efficient results, okay. So you can actually follow this course. It covers all the topics here, and you can see that this is the flow which we will be following. Okay, so this is a paid course and you can purchase it by signing up here. Okay, so that's it for today. If you have any doubts, you can message me on the live chat on any of my videos, or you can contact me on LinkedIn. Harshal Jain is my username. Okay, so that's it for today. I will see you in the next one. Till then, see you. Have a good day. Bye bye.